Welcome back everyone. In this lecture we are going to see the restriction and the induction of representations. So, let me first start with restriction, which is easy to define. So, let us say we have a subgroup H of G. So, G is finite group and H is subgroup of G. So, now we take some representations of G and then we want to talk about the restriction of that representation to H. So, let us call this rho V, which is a representation of G. So, now what we can do, like given this representation, we can actually restrict this rho V to H and then see this. So, you take this rho V, which is a representation of G, which acts on capital V. So, now from this what we can do, we can actually look at this restriction map to H. So, this is indeed again a group homomorphism from H to this GLV, and this restriction is what we call it as restriction of restriction representation. So, sometimes we denote this by restriction of G to H of V, and then sometimes we also use this other notation restriction of G to H rho V. Okay. These notations are used to denote this rho V restricted to H. So, the restrictions are somewhat very easy to define. So, it is the representation given by the same vector space V. So, under the action only changing. So, the action given by the restriction map rho V restricted to H. So, we are not changing the representation space. So, the representation space stays as V, but the action is restricted to H. Okay. So, there is another class of natural representation called induced representations or the inductions, but they are somewhat difficult to define and understand. So, maybe we will spend more time in defining and understanding these representations. So, as before we take G to be finite group and then H to be subgroup of G. So, now how the induction works, we start with the representation of H and then induct that representation to G. So, let us say I have this representation W, which is given by this map rho W H from H to GL W. So, this is let us say given representation of H, and from this what we want to do, we want to go to representation of G. Okay. So, that is what we call it as induced representation. Of course, when you are interested in getting representation of G, the representation space itself you are supposed to change. There are many various definitions of this induced representations. So, let me start with the definition that involves W valued G functions. So, very explicitly, so let us define what is this space. So, the space ind G H W. So, this is going to be, you take all possible functions from G to V, they are G to W, they are W valued functions from G satisfying the following conditions. You take f of H x. So, that is supposed to be equal to rho W H of H acting on this f of x, and this is true for all x in G and H in H. Okay. So, this is the defining relation of this space. So, basically it is a function space satisfying some properties. So, let us actually look at how this relation can be simplified. So, if we forget this rho h w and then simply write the action of h by the dot action, then the equation that is in this box can be read as follows. So, you take this f of h x, you are demanding that. So, the action of h should commute with this in some sense. So, then you get exactly f of h x equal to h dot f of x for all x in G and h in H. So, this is what you are demanding. So, now note that this is indeed somewhat puts lots of restriction on the function, and if you think about it, the function is completely determined by the right coset representative of H. So, maybe in a minute I will come back to that. So, now I am going to define the action of G on this this induction space. So, let us define this action. So, the G action, so that is defined as follows. So, you take G in G and F in this induction. So, then the G of F, which is again a function from G to V, sorry G to W. So, this is defined to be take G of F, apply it on some x. So, it is given by the right translation of this action of G. So, you look at f of x G. So, that is the value it takes when you apply G of f of x, and this is how you define for all x in G. So, basically here we are actually looking at the right translation. Okay, so let us verify that this is indeed gives us well defined action of this G on this induction space. So, here is the proportion. So, the above action is actually, so this is the action we are talking about, the star. The G action given in star defines a G representation on this induction. Okay. There are two things to verify. First of all, we need to verify that G of f is again element of this induced space, and then when you apply the elements of G, the group multiplication also preserved in the action. That is what we need to verify. So, let us verify one by one. The very first thing is to do for f in this space and G in G. So, we claim that G f is again element of this induced space. So, for that we need to verify that G f of h x should be equal to h dot of G f of x. So, just rewrite this. This is what we need to verify. So, on the left hand side what we have, so G f of h x is going to be by definition f of h x g, which is exactly equal to h dot of f of x g, which is exactly equal to h dot of G of f of x. Okay. So, that actually verifies this. So, that means this claim is verified. G of f is again element of this induced space. So, now the second thing is the action is indeed G action. So, for that let us take G dash from G, and then f is from this again the induction. So, then look at G of G dash of f and then evaluate at x and then see what happens. So, this is exactly equal to G dash of f of x g, which is exactly equal to f of x g g dash, which is exactly equal to g g dash of f of x. So, this proves that g of g dash of f is exactly equal to g g dash of f. So, this proves that the action that we defined is indeed G action and the induction is indeed G representation. Okay. So, now let us try to understand what happens to this space. So, we are going to actually give very explicit basis that is going to tell us that the structure of this space and the dimension of the space and so on. So, for that let us fix some right coset representatives of H inside G. So, let us label them as G1 etc., let us say Gk. So, this is the set of right coset representatives for H in G. Usually it is denoted by G like this mod H. Okay. So, now in particularly I can write G as H G 1 disjoint union etc., disjoint union H G k. So, now given any element x in G, there exists unique pair G I comma H, where it comes from this representatives. So, let us call this representatives x cross this capital H, such that this x becomes H G I. Okay. You will be able to write any given element as product of element from capital H and this coset representative G I, and that tuple G I H will be unique. So, now that tells you that what will happen to this function f of x. Suppose if you start this f from this induced space, so then you can see that when you evaluate f of x, that is going to be exactly given by f of H G I, and which is given by the action of H on f of G I. So, as far as we know what is the value of this f of G I, using the H action we will be able to recover all other values on the coset, right coset H G I. That is what this equation actually tells. Okay. So, basically the observation is that f restricted to H G I is determined by f of G I and H action on f of G. So, this is what we are getting. So, in particularly we are allowed to make any choice for f of G1 etc., f of Gk, and rest of the function that will be determined uniquely on G using the action of H on W. Okay. So, we can make any choice for this f of G1 etc., f of Gk. So, that is going to be W valued elements. So, then the rest of the function determined uniquely. Determined uniquely on G, and of course, using the action of H on W. So, the thing is we are actually assuming that we know everything about the H action of W, H action on the W. So, using that action, so we want to recover the induction space. Okay, so let us elaborate this bit more and then write down very explicit basis for this function space. So, we for that purpose we fix a basis and call that as W1 etc. WD of this capital W. So, now let us say the D is the dimension of this W. So, now what we can do for given I from 1 to k and then j from 1 to d. So, we define these following functions, call it as f I j, and it takes the value on h g r. So, this is given to be, it is exactly given by h acting on w j if r equal to I, otherwise it is just 0. So, basically what we are telling, so f I j just sees that gith coset. So, rest of the coset it is 0. So, basically f I j of any x is 0 if x does not belong to h g I, okay. And when it is inside f I j inside that coset, h g I is given by h dot w j. So, this is how it is defined. So, now it is not difficult to see that by definition f I j they are all elements of this induced space. Actually, we claim that this is indeed gives us basis. So, this f I j where I runs over 1 to k and then j runs over 1 to d. So, this form a basis of this induced space. Indeed, what we can do, we can actually fix I and then look at the span. So, the span of f I j where j ranges from 1 to d. So, this is indeed a copy of actually w inside this induced representation. So, as a vector space it is clear that this is indeed isomorphic to w for each I in from 1 to k. So, indeed we have like k copies of w inside this induced representation. So, one can actually think that so if you denote this by w I, so then once we prove that this is a basis, then it is immediate that this space, the induced space will be decomposed as direct sum of this w I ranging from 1 to k. So, this is what we are getting it for free. Okay. So, this w I maybe you can also denote it by w g I because it is kind of determined by that coset representative g I. So, that is the observation. So, let us prove this claim. From this it is clear that what we are actually talking about. So, maybe like I can actually give another definition of this w I. So, observe that this w g I, this is those functions that you can take it from this induction space such that when you look at the values of this function outside this coset h g I, you demand that to be 0. So, f of g is 0 for all g not coming from h g I. Okay. So, then indeed we claim that so it will follow from actually maybe I will leave it as exercise because inbuilt in the proof that the span of f I j where j ranges from 1 to d is indeed going to give us w g I. Okay. So, this indeed proves you can also further factorize. If you combine these two results, then this induction can be factorized as a direct sum of w I. Okay, so let us prove directly that this Fij they form a basis, then from that these statements will become very clear. So, to prove they are bases, we need to prove two things. One is they are linearly independent and they also span any element of this induced space. So, let us first check it is linearly independent. So, linearly independent, it is very simple. So, let us say we have a relation Cij Fij equal to 0. So, then now what we can do, we can fix some I naught coming from 1 to k, and then we can evaluate this f at that g I naught. So, take f of g I naught, evaluate and then see what happens. If you evaluate, what will happen? This is on one side you get 0, on the other side you get it is exactly Cij Fij g I naught. But recall the definition of Fij. So, Fij defined to be, it takes value 0 on all elements not coming from this Hgi, and on Gi it takes exactly Wj. So, when H is identity, you get Fij Gi equal to Wj. So, that is what we are going to get it here, and if you use that, you see that this is exactly equal to summation. So, I should be equal to this I naught. So, you get Ci naught j and then Wj, where j varies from 1 to d, and this is indeed 0. But since Wi's are actually basis for capital W, that would imply that Ci naught j is 0 for all j, and since I naught is fixed randomly, so that would imply that Cij is 0 for all Ij. So, that proves that this Fij's they are linearly independent. Now, let us verify they are indeed bases. So, let us take f from this induction space. Now, what we can do? We can actually fix some x in Hgi and then see that how one can evaluate this f of x. So, f of x is going to be f of Hgi, where you write x as Hgi. So, then this gives us exactly equal to h dot f of gi. So, now what we can do, we can rewrite this f of gi in terms of the basis elements. So, you rewrite this as some aij fij of gi, because this fij gi is nothing but wj. So, this tells us that what should be the f. So, now it is easy to see f is exactly sum over ij aij fij. Why this is true? Just take this x and then just evaluate. So, if you write x equal to h g I naught, you can see that f of x is exactly equal to summation aij fij h g I naught. So, now whenever I naught equal to I, this is going to survive, otherwise it is going to give us 0. So, then this implies that f of x equal to summation a I naught j f I naught j h g I naught, but this is exactly equal to summation a I naught j h dot w j. So, now if you look at the value of f of x, you can see that this is what we will be getting, because this is exactly equal to h dot summation a I naught j w j, but this term is exactly our f of g I naught. Okay. So, that is the way we indeed constructed the function. So, that actually tells you that this f is indeed written as follows. Okay, this proves indeed this Fij formal basis. So, now it is a simple observation to see that once you fix I and then vary j, so then you will be getting this Wgi. So, in particularly the induction space is direct sum of this Wgi, I range from 1 to d, sorry 1 to k. So, now Wgi is naturally isomorphic to W because there are only d elements that spans. So, this tells us that what will be the dimension. So, the dimension of this induced space is exactly equal to k times d, which is exactly equal to the cardinality of G divided by cardinality of H times the dimension of W. So, this is what we have proved. Okay. So, now let us actually compute what is the trace on this induced representation. So, here is the trace calculation. So, recall that how one actually computes the trace. Suppose if you have a V vector space spanned by the basis elements etc. V1 etc. Vn and T is a linear operator from V to V, you write Tvj as summation Aij Vi, and then the trace of T is going to be sum of this Aii. Okay. All the diagonal entries you take and then submit, that is what called trace. So, that is what we need to do it for this particular induction, but note that induction already has this Fij as basis. So, this is the basis where I runs over 1 to k and then j runs over 1 to d. So, this is the basis of our induced representation. So, now let us use the action of G on this and then see how we can compute things. So, let us say G comes from G and then we want to compute what happened to G of Fij. So, now what we can do, we can write this G of Fij in terms of the basis elements. So, write it as summation A R S F R S, where R and S runs over. So, set rho to be the induction, G to H, rho of H W. So, now this is the induction representation. So, if you just take this equation star and evaluate at some G I naught, let us see what happens. So, G of Fij. So, let us evaluate at G I because these ij's are fixed. Okay, these ij's are fixed. If you apply it on G I, you get exactly summation R comma S A R S F R S G I. But recall that F R S G I is going to take exactly value W S when I equal to R, otherwise it is going to be 0. So, this you can rewrite as summation A I S F I S on G I, which is W S, where S is running over from 1 to D. So, this is the value that we get. So, now what would happen if this G I G G I inverse is not an element of H? So, then we know that so this is going to be equal to F I J G I G. So, this is exactly equal to summation S range from 1 to D A I S W S. So, now you can see that Fij is indeed 0 outside Hgi. So, that forces that this Gig must be inside Hgi, otherwise this value is going to be 0. So, we will have two cases. The case 1 is that Gi inverse is not in H. Okay. So, in that case you can see that Fij Gig, so this term, so this is going to be 0, Gig, so this is going to be 0, and that gives, this is exactly equal to Ais Ws S range from 1 to D is 0. That would imply that Ais is 0 for all S, but the coefficient of Fij is going to be Aij. So, that implies that Aij is also 0. So, that means no contribution will be there for the trace value, okay, because we are looking at the coefficient of Fij inside this, which is Aij. So, now look at the second case, the case 2, when Gi inverse is in H. So, let us write it as H. So, then that would imply that Gig is exactly equal to Hgi. So, now if you evaluate this G of Fij of Gi, so this is going to give us Fij, sorry, Fij Gig, which is exactly Fij Hgi, which is exactly rho H rho Wh of H acting on this Wj. So, this is what you get it on the left hand side, but what will be on the right hand side? So, on the right hand side you have summation Ais Ws. Okay. So, that means this rho Wh acting on this Wj is going to be equal to summation Ais Ws S range from 1 to D. So, this is what we are going to get, okay, because this is exactly equal to summation Ais Ws S range from 1 to D. So, now you can see that these coefficients Ais, they are indeed coming from, you can actually look at this operator H acting on this capital W, and when you write this H acting on this Wj as a linear combination of Ws, so the coefficients Ais are the coefficients of that matrix rho Wh. So, rho H W of H, this matrix is exactly Ais. So, now that means, so there is a close relationship between Aij and this matrix of this. Okay. So, what will be the diagonal thing that we will be interested in? So, let us look at the contribution of this Aij. So, the contribution comes from Aij, which is indeed calculated from the action of H on W. So, now that tells you that if you are interested in the trace of rho g, so you will be getting so from this you can see that so we are interested in actually computing the trace. So, we wrote G of Fij as summation Ars Frs. So, in particularly the trace of rho g is exactly going to be the sum of Aij. So, sum of Aij, because the Fij coefficient is Aij here. Okay. So, that is the thing. So, now if you are interested in looking at this Aij, so look at this operator H acting on W, then the diagonal entry of this, okay. So, this operator rho W h of h. So, what will be the ijth diagonal entry? So, then we will be looking at exactly wjth coefficient of this, which is exactly aij. So, from here you can see that aij is nothing but comes from this diagonal entry of this matrix. So, that tells you that when you look at this ith block, so this trace of rho g, so depending upon this ith block, so the sum runs over all the ith blocks, where we have this constraint that gi inverse should be coming from this h. So, then all you do is this sum is going to be the trace of this rho w h. Okay. So, that is what we are getting. So, but what is that trace which is given by this character value chi w of h, but h is, if you read it from the previous relation. So, this is the relation that we have. H is, from this you can conclude that h is exactly gi inverse. So, then if you write everything in terms of gi, you can see that so this is exactly equal to sum over all I such that gi inverse is in h, and you take the character of this gi inverse. So, this is what you get it as trace. So, that means the trace of this induction induced representation so this is at the value g is given by summation, you run it over all I such that h g equal to h gi, where you take chi w of gi inverse, and it is an easy exercise to rewrite this. So, I will leave it as exercise. So, you can rewrite this as 1 divided by the cardinality of g summation chi w x g x inverse, where x runs over g such that this x g x inverse is comes from capital H. Okay. So, this is another way of writing the same induced character, and this actually kind of completes the calculation of the induced character. Okay, I will stop here, and then so in the next class what we are going to do, we are going to actually prove the Frobenius reciprocity theorem that actually relates the character of the induced representation and the restriction representation. Okay, I will stop here. Thanks.